Today we will speak about matrices. First of all, let me define what is a matrix. So, definition. So, matrices are rectangle arrays of numbers. For us, it will be usually real numbers. And this array is between brackets. Okay, so for example, we could have, so we will usually denote the matrix by a capital letter and then round bracket and some numbers, for example, -2, 4, 5, -3. Another example, so it doesn't need to be square. It could be also a rectangle, 1, 3, -2, 4, -1, -5. This is another example of matrix. Now, we denote mat and in subscript m times n with coefficient in R, okay? This will denote the set of all matrices with m rows with n columns and with real coefficients. Okay, so for example, let's see. With our previous example, A will be typically an element of mat 2 by 2 with coefficients in R. And B, so in the case of B, we have 2 rows and 3 columns. Therefore, this is an element of, so 2 rows, 2, this is the number of rows, and this will be the number of columns, so 2 by 3 in R. So, matrices, why do we study them? Matrices are used in math, but not only in math, they are also used in physics, engineering, statistics, basically they can be used for two main purposes. The first one is to solving systems of linear equations. So we will see that what means systems of linear equation in the next chapter. So I will not explain today what is this. And they can describe, so useful for describing transformations transformations of the plane or 3D space. Okay, let me give you an example of the second application. So imagine that we want to describe the reflection against the y-axis in 2D. Okay, so what does it mean? We can draw our so this is x-axis, y-axis. Now, what is reflection with respect to the y-axis? So if we are given a point P with coordinate x and y, then the reflection with respect to the y-axis will be the point here, right? So let's call it R of P, and its coordinate will be, as you can see, minus x and the same y. Okay, so how to represent this kind of operation on the plane? Well, it's very simple. First of all, this map R will be an operation in the 2D space, from the 2D space to the 2D space. So the 2D space, two-dimensional space, we can represent it by the set R times R. What is the set R times R? Well, this is the set of pairs of real numbers, so I call them x and y, and I can see that as the coordinate of my point P. Then this function will go again to the plane, so I will have again R times R here, and it sends the pair xy to the pair minus x minus y. Okay, so this is a function of two variables, right, that I can see as a transformation of the plane. Matrices can gather the whole data of this function in an easy way that I would like to describe. So how do you associate to this data a matrix? Well, it's very easy. You do the following. So I'm going to associate to this a matrix. Here I'm going to take the coordinate of the vector. So I work in the standard basis, Oij. Remember that if I have this Oij, I can talk about the coordinates. So in this first column, I will give the coordinates of R of I. In the second coordinate column, I will give the coordinates of the second vector of my standard basis, R of j. Okay, so what are the coordinates? Well, notice that I is a vector with coordinates 1 times I plus 0 times j, right? So I consider this I as a vector with coordinate 1 and 0. So my function R will send this vector I 1, 0 to what? It will send it to, as you can see, minus 1, 0. On the other hand, vector j is a vector with coordinate 0, 1, and therefore it is sent by the same function to the vector with coordinate 0 and, you see, minus 0, which is 0, and 1. So the same, actually. Okay? So basically, my matrix here will be the matrix. So I remove this here. So here, first, in the first column, I put the coordinate of r of I. This is r of I. And this is r of j. So I get -1, 0, and here I get 0, 1. Okay, this, we call that the matrix associated to R, and we denote like this. So this matrix, we will see this a little later, represent the whole data of this function. You can understand the whole function by just these 4 numbers. Okay, we will come to that point a little later. Let me precise a little more the notations we will use. Okay, imagine that we have a matrix M in mat M times N R. We want to describe the numbers that are inside this matrix. So M will be a matrix with some entries, so-called entries, and usually we use a small letter and we put in subscript 2 indices. The first one refers to the row number, and the second index refers to the column number. Therefore, for example, yeah, so if I call it M, why don't I call the entries M, okay? And now the first index will be 1 because I'm in the row 1, and the second will be column 1, so M1, 1. Now what is the second? Second, I don't change the row, so it's same row, so it will be 1, but this time second column. Okay, so M1, 2. Now 3 dot, I want to guess what is the last entry here. So the last entry, so this is called an entry. Entry. What is the last entry here? Well, first row, isn't it? Now it's the maximum number of columns here, the last number. So this number represents the number of columns, so it will be M1n. And I can close my bracket. Okay, here again, I'm going to do 3 dot. Now, the last coefficient on the last row, it will be the row number M. So it will be, yeah, I see the problem. Okay, so, because you see, we will have 2M, which is not convenient. So let's call this matrix A. Okay, we're going to call it A. And we will call the entries A, like this. Yeah. So this is a common problem in matrices. You have to choose a good denomination for the letters. Okay, so be careful with that. Okay, so the last was AM, and then what is the column? It's 1. So AM1. Okay, here was A, 3 dot, and finally here will be AM and N. Okay, final row and final column. You can also summarize this. If you want to be a little less precise, you will write AIJ. Okay, usually we will choose as indices I and J. Okay, and if you want to precise a little more, you can say that I goes from 1 to M and J goes from 1 to N. Okay, this is a little precise form, but sometimes we will just write AIJ. Okay, this is a notation in the matrices are very important actually. Little more definition. So a matrix with M equal N is called a square matrix. Okay, so square matrix. Also, if M belongs to mat M times N, this M times N is called the size of M. Okay, so definition, a matrix 1 times N is called a row vector. Row vector. So we have only one row and n columns. So such matrix, for example, will be something like, so one row and 1, 2, 3, 4. Okay, this is an example of a row vector. Similarly, you can define a matrix. So with m rows and one column, so this is called a column vector. Column vector. So for example, so this time you will have something like that. 1, 2, 3. This is column vector. Okay, these are basic definitions and notations. Also, maybe I want to define some very special matrix. So we denote IN. This will be the matrix with on the diagonal, so these are called the diagonal entries, we will put only 1. And then, just after, we will have only zeros. So here we will have 0, 0, 0. So you put 1 on the diagonal and everywhere else 0. The n means that this matrix is an element of mat n times n. So this matrix is a square matrix. So this matrix is very special and it's called the identity matrix. Another very special matrix is, we will denote 0 mn. Okay, this will be a matrix in mat m times n, and it will be defined by putting just only 0 entries. So the whole matrix is full of zeros. Then we will call this the m times n 0 matrix. So be careful, identity matrix must be diagonal, but I mean square matrix, but the 0 matrix can be anything, any numbers of rows and columns. Now that we have defined a set of all possible matrices, we are going to define operations on matrices, like we did for vectors. So first of all, let's talk about additions. So operations first. We will talk in this section of operations on matrices. operations. First, we are going to consider addition. So, the input will be two matrices of same, this is very important, same size, let's say m times n. The output, okay, so let's call these matrices A with coefficient entries Aij and B. Okay, so you see, here the matrix, first matrix is called A. Therefore, I will use a small letter A to talk about its entries. If I pick a second matrices, then the entries are different. I will use again the small letter B this time to talk about the entries. The entries. Now, what about the indices? Indices are these little numbers here, letters here. Because A and B have the same size, I can pick the same letters. So here, the entries for B, I can call it I and J. Be careful that if B was of a different size, I would have to change these letters I and J. I would pick some other letters. We will come to this point a little later. So anyway, when I fix the notation here, I will fix like this. Now, what is the output? Output will be a matrix that I will denote A plus B, and it will be again a m times n matrix. Okay, so if I want to define this operation, addition, I need to define the entries of what is the entries of this matrix, this new matrix A plus B. This is very easy. So I put as a definition that the matrix A plus B will be matrix with m rows and n columns given by the following formula. I will just add component by component Aij plus Bij. Okay, let me give you an example. What means this formula? Okay, example. Imagine that I have 1, 2, 3, 4, and I want to add. So I have to take another matrix with same numbers of rows and columns. Therefore, let's say 2, 4, 6, 8. Okay. Now I can do this operation. If this matrix had a different size, I won't be able to do the operation. Now, how is done the operation? The operation is given by this formula. It means that I'm going to add component-wise, component by component, which means that here I will get 4 coefficients. Now, how obtain this coefficient is as follows. You pick this first coefficient in the corner, 1, and you have to add it with this one, so in the same position. So 1 plus 2. This one, 2 plus 4. This one, 3 plus 6. And this one, 4 plus 8. Therefore, in this case, the matrix is just 3, 6, 9, and 12. Okay, this is the operation of addition of two matrices. Let's see another operation. The second operation is scalar multiple of a matrix. Here the input is a matrix A with entries Aij that will be in some set of matrices M times n with coefficient in R. And I will take another input, a scalar, so an element lambda in the set of all real numbers. The output will be a matrix that I denote lambda dot A, and so this will be a matrix of the same size as A, m times n, and it will be defined by the following formula. Lambda A will be equal to lambda Aij, isn't it? And definition, what is that? Well, this will be just a matrix with coefficient lambda dot Aij. Some exercise for you. Okay, so if we consider the matrix 2 by 2 A with entries 3, 1, minus 2, 5, and B 2, 1, 4, minus 1. Okay, we can consider this. Please compute A plus B, A minus B. So what is A minus B? This has to be understood as A plus minus 1 times B, right? And you will compute also 2A plus 2B and 2A plus B. That's right. Okay. Now we want to study properties of these two operations with each other. Okay, so we have the following proposition. So we consider A and B, two m by n matrices, and we will also consider lambda a scalar. Now we have the following proposition. First of all, A plus B will always be equal to B plus A. The second property is that if you do lambda dot A plus B, this will be equal to lambda A plus lambda B. 3. A plus the zero matrix. Okay, so here A belongs to n times n, so it's the 0 n times n matrix. This will be equal to the zero matrix plus A, and this will be equal to A. Okay, so here let me prove, for example, let me give the proof of let me give the proof of 1. Proof of 1. How do we prove 1? Okay, so on the left-hand side, we have A plus B. Now, what is A plus B? It will be Aij plus Bij. The matrix with entry Aij plus Bij. But this is by definition of plus operation. Now, I can use a property of real numbers. Real numbers satisfy the following properties. A plus B is always equal to B plus A when I have two real numbers A and B. Therefore, I can deduce that this Aij plus Bij is in fact equal to Bij plus Aij. So here it's really a property of real number. And then, using again definition of plus, I can write that this matrix is in fact the matrix B plus A. Okay, so an exercise is proof 2 and 3 by following the same model. Basically, the proof of these assertions 1, 2, 3 results from the definition and from the properties, analogous properties in R. Okay. Let's study a third operation on matrices. The third operation I want to study is matrix multiplication. So this operation is slightly more difficult. What is the input? Input will be two matrices with the following condition on their size. So not any two matrices. For example, if I start from A, Aij, with entries Aij, a matrix in M times N. Then, okay, what kind of input I want to calculate? Imagine that I want to calculate A times B, A times C, like this, and it will be denoted with a dot, or it can also be denoted without dot. You can just write AB. Now, in this case, I have the following condition on the size, and it will give a condition to the notation on the indices. You will see that. So, if I start with n rows and n columns on the left, then on the right hand side, I must absolutely have the following condition. The number of rows of B should be the number of columns of A. So here I need to put an n. This is my condition. Now, what a number of columns on B is, there is no condition on that, which means that it can be anything. But anything means it can be m, it can be n, but it can be also different of m and n. So we will use another letters. For example, I will use the letter N, L. Yeah, I will use the letter L. Okay, these are the consequences. The consequence on the notation of the entries of B. First of all, I choose the small letter B because my matrix is named after capital letter B. So the entries are small letter B. Now, the index for the number of rows. Okay, the number of rows is the same as the number of columns of the first matrix. So here I need to take this index, J. Okay? Here I picked another number for the numbers of columns, and I call it L. So it cannot be I cannot choose I here for the number of columns, and I cannot choose J. I need to choose a new letter, so let's call it K. Okay, so what is the definition of this new matrix, which is the multiplication of A by B? So this will be a matrix with the following entries. I will call the entries temporarily C. Okay, so here the result is that it will be a matrix in mat M, L, which means that the first index should be the index relative to M, which is I. here I put I. The second index should be relative to L, and this index is K. So I should call the entries CIK. Now I need to define what is CIK. CIK will be the sum. So I have three indices, I, J, K. Here, I and K are fixed, which means that here I'm going to do a summation not on I and K, but on the remaining index, which is J. Okay? So J will go from 1 to what? Well, J is the index chosen for the number of columns of the first matrix. So it goes maximum to the number n. And then I will just pick A, I, J, B, J, K. Here, it's a multiplication. That's right. So this is a formula, but you can also compute this visually by your eyes. So basically, okay, you have two matrices with a number of rows, and so for example here, let's say that you are considering the ice row. So it means that here you will have AI1, AIN. Okay? And then let's say that you consider the case column. So here we go. This will be B. So here it will be 1 and case column, so K. And the last one will be what? So B belongs to NL. So the last row is N, and column is the same, NK. Okay, so you will fix I, NK, and then how do you calculate CIK? You will multiply this row by this column in the following way. So CIK will be AI1 times B1K plus, what is the second here? The second is AI2. And what is the second here? Times B2K. Okay, so you see how it goes. So the last one, what will be the last one? The last one will be, so it will be again AIN times BNK. That will be the final term. Okay, all these formulas are correct. So try to pick the one you understand the best. For example, let me give you an exercise. Calculate. So you are going to calculate the following product: 1, 2, 3, 4, 5, 6, 7, 8 times 0, 1, 3, minus 1, 4, and minus 1, minus 2, 4, 2, and 2. Okay. So please try to calculate this. Now, let's see a special case of the operation of multiplication. We are going to see the special case of the multiplication of a matrix by a column vector. So So this is a special case of matrix multiplication. Okay, so we start from a matrix A and J, a matrix with m rows and n columns. Now, if we want to multiply this by a column vector, what does it mean? It means that here I have size m times n, and here I must have also n, the same number as here. And because it's column, it means that there is only one column. So it will be necessarily n times 1. Okay, so let me call this x1, xn. So if I apply the previous formula, I will get as as a result, you see, you just simplify this, and you will get in fact, n times 1 matrix. The first entry will be a11x1 plus 3 dot a1nxn. You can check that. I just follow the definition of multiplication of matrix. The last one will be am1x1 plus 3 dot amnxn. Okay. Now let's come back to the case of a reflection against the y-axis. So remember, we had this map from R2 to R2. Sorry, by R2 I mean R times R. Okay, this is definition. Now remember, this map was defined like this. To x and y, I associate minus x and the same y. Now remember that I said that we can associate to this operation of the plane some matrix, and this matrix was denoted mat R. So what was it? It was obtained by putting the coordinates of the vector of the standard basis ij in the column. So the first column was r of I, which was -1, 0, and the second one was r of j. R of I, this was r of j, and this was 0, 1. Okay, so you understand that this is actually equal to r of xy, right? Well, let's try to do this computation. We are going to multiply this matrix by a column vector xy. What do we get? We get -1, 0, 0, 1, x and y. Okay? So, what will be the result? The result, so this is a 2 by 2 matrix, and this is a 2 by 1. The result will be a 2 by 1 matrix. So it means 2 rows and 1 column. So it's again a column vector, which means that here I have to find 2 entries. How do I find the first one? Well, let's use a visual interpretation of the formula. I'm going to consider this first row, and I multiply it by the only column that I have. Okay? What do I get? I get -1 times x plus 0 times y. So altogether I get only -x. To get the second entry here, I multiply the second row, so 0, 1, by the only column. So I get 0 times x plus 1 times y, which is y. Okay, what do you observe? You observe that this function, r of xy, is completely expressed by this matrix, because so the value r of xy is minus xy, and it's exactly the multiplication of the matrix associated to r by the column vector xy. That's why the matrices, these matrices of 4 numbers, minus 1, 0, 0, 1, represent the whole data of this function. That's very useful. It's a way to make the information very compact. Okay, in fact, you can do that for any application which is so-called a linear transformation. Linear transformation. T. Okay, so what is a linear transformation? Imagine that you have a function from r squared to r squared, and you will associate to x and y. You will associate some vector, column vector with coordinate ax plus by and cx plus dy. So this is called the linear transformation. Whenever you have this kind of transformation, okay? So basically, you cannot have x squared. This is impossible. You cannot have cos x plus sin y. This is also forbidden. You can only have these kind of terms. Then mat t, in this case, will just be a, b, c, and d. Okay. Let's check this. Indeed, so if we do the product a, b, c, d with x times y, what do I get? I will get a times x plus b times y. A times x plus b times y. And here I will get c times x plus d times y. Yeah. So as you can see, this works not only for the reflection, but for all functions of the plane, or it works also in 3D actually, for 3D, for R3, whenever you have this kind of function, okay, with linear expression. Exercise. What is the matrix associated to the reflection with respect to the x-axis and with standard basis? You will use a standard basis again, so I and j, Oj. Now you can do the same also for what is the matrix associated to the symmetry with respect to the origin. Okay, so what is the symmetry with respect to the origin? If you have a point P, then you will take it symmetric with respect to the origin, S of P. Okay? So what is the matrix associated to this operation? You can think about it. Right. So, we have still time. So, let's study another operation. First of all, let's study the properties of this new operation of multiplication with respect to the other. So properties of the product with respect to the previous operations. Right, so first of all, we have the property called distributivity. Distributivity, what it is? Well, it means the following. A times B plus C is equal to AB plus AC. And also I have B plus C times A will be the same as BA plus CA. This is distributivity of the product with respect to addition. I have also distributivity with respect to the scalar multiplication. So what is lambda A times B? Well, this will be equal to A times lambda B. And this also will be equal to lambda times A times B. Okay, so I have these properties. Another property is the so-called associativity. It says the following: A, B dot C will be equal to A dot BC. This is associativity. So maybe I put a danger sign here. A times B is not in general equal to B times A. And even more, B times A might not be possible. Example, or exercise. You are going to calculate the following matrices. So let's consider A equal 1 minus 2 and B equal 1 minus 1 minus 3, 2, and C equal minus 2, 1. So you will check that AB times C is indeed equal to A times BC. Okay. You will check also that AC exists. It exists because it's a, you see here it's a 1 times 2 columns, and here I have 2 rows times 1, so this is fine. And CA also exists. Right, try to check this. Another operation is called operation of transposition. Transposition. Okay, let me give you the definition of this operation. Let A be a M times N matrix. So we can call its entries by Aij. The transpose of A denoted A with in exponent a capital T will be the matrix with a coordinate with entries, small a with capital T and indices Ji. And what is A, J, I, T definition? It will be just A, I, J. So example, if you take a row vector, so 1, 2, 3, what is A transpose? A transpose will be just the matrix, sorry, it was a column vector. It will be the row vector 1, 2, 3. That's what it does. It transforms the operation of transposition, transform rows into columns. Okay. Now, what are the properties of the transpose? Well, the first basic property is that if you transpose twice, then you will get the same original matrix. The second is that A plus B transpose will be equal actually to A transpose plus B transpose. No worries with that. The third property is that the transpose of lambda times A will be actually lambda times the transpose of A. The fourth property, be careful, it's a little more tricky. What is the transpose of a product? Well, here you have to reverse the order of the term. So it will be B transpose times A transpose. Exercise. You can check condition 4 with A equal 2, minus 1, minus 2, 3, and B equal to minus 1, 3, 4, 1. Okay. After seeing this series of operations, I would like to give a little more terminology on matrices. So let's call this section special types of matrices. First of all, as you remember, we have seen the notion of square matrix. Okay, a square matrix will be n times n matrix. Okay. Now, a new type is a so-called upper triangular matrix. Okay, what is that? First of all, the upper triangular matrix is a square matrix. It's a square matrix, A equal Aij, such that Aij will be equal to 0 whenever, so for any I greater strictly to j. An example of this is the matrix minus 3, 7, 6, 0, 1, 0, 0, 0, minus 1. Okay, so the important is that if you consider the diagonal, here you can draw a triangle. A triangle, so this will be considered as upper triangular. Okay, everything below the diagonal must be 0. Now we have also the notion of lower. Yeah, maybe we can shorten this as upper triangular. Yeah, upper triangular. And we will have lower triangular. Lower triangular will be a matrix Aij such that we will have Aij equals 0 for any I, this time smaller than j. And visually, this will be always something like that. This is the diagonal entries, and here you will have only zeros. Okay, this will be lower, this will be upper. Another type of matrix will be diagonal matrices. Okay, so what is a diagonal matrix? Diagonal matrix, let's call it D, Dij. This will be a matrix such that Dij will be 0 whenever I is not j. So for example, any identity matrix is diagonal. Also, the 0 matrix n times n is also diagonal. Right. Okay. And we will call invertible matrix A is, so this will be a square matrix Aij such that there exists a matrix B square, same size as A, such that we have the following: A times B will be equal to B times A will be equal to the identity matrix. Any matrix satisfying this will be called invertible. When A is invertible, the B satisfying star is denoted A to the power minus 1, A to the minus 1. Remark that such B is necessarily unique. We will see that invertible matrices play a very, very important role in the future. Okay, now that we have seen these types, let's see the following properties. The first property is that if AB is square, respectively upper triangular or respectively lower triangular or respectively diagonal, then so is or invertible even, diagonal, sorry, so diagonal respectively invertible, so is AB yeah. Good. Another property is the following. If you take a 0 n times n matrix and you multiply by n times n matrix, then this will be equal to A times your 0 matrix n times n, and this will be always equal to the 0 matrix. Another property is that if A is invertible, so is A minus 1. N minus 1 will be also invertible. If A is invertible, so is lambda times A. For any lambda which is not equal to 0. properties 5, if A is invertible, so is A transpose. A transpose will be also invertible, and moreover we will have A transpose. So what will be the inverse of A transpose? It will be A minus 1 transpose. Okay, so exercise prove these properties. It's very good exercise. Let me give you an example. If we want to prove of 5, if we want to prove 5, then basically we need to calculate A transpose times. So we are giving here the inverse. The inverse should be this one. Okay. So what does it mean that this will be the inverse of this? It will mean that we should have this equal to the identity. This is the question. And we should have also this product is also equal to the identity. Okay, so we need to check both. How do we do that? Well, we use the properties of the transpose. So we know that the transpose, a product like this, how is it done? Well, it's easy. You have to reverse the order. So this will be equal, in fact, to A minus 1 times A and then transpose. This is by property of transpose. Okay, but this is by definition the inverse of A. So definition of A minus 1 gives us that this product is in fact the identity. And then I transpose. Okay, but what is the identity? Identity is a diagonal matrix with 1 in the diagonal and 0 as other entries. You can check very easily that if you transpose this matrix, you will get actually the same matrix. So the transpose of the identity is actually the identity. So you get your first equality here, you get 1, this prove 1, and to get 2, well, this is basically the same. So A minus 1 t times AT. This will be by the property of transpose. This will be equal to A times A minus 1, this time transpose. Again, by definition of A minus 1, we know that A times A minus 1 is the identity. And so we can conclude as before. This proves 2. Okay. So, as you can see, we proved number 5. So you can try an exercise to prove the other assertion. Okay. I think, yeah, one more theorem, which is quite useful. Theorem. Let A, B, C, and D be square matrices with A invertible, then first of all we have the so-called cancellation law, which says that AB, if AB equals AC, then we can conclude that B will be equal to C. The second condition is that if AD equals a zero matrix, then this implies that D is a zero matrix. Okay, I will stop today's lecture here. Thank you very much.